parameters, the benefits of nonlinear device models.
Can you hear me? All right, there we go. All right. Well, I'm the last speaker of the day, which puts me in the honored position of trying to get everybody out on time. So I'll do the very best that I can and not keep you too long. First of all, I'd just like to thank AWR for allowing me to speak. I'm actually a professor at Macquarie University, and they gave me the opportunity to take this this spot that they had in the micro app. So I want to acknowledge that to them. So what I'd like to do today is talk about models in general, and by way of talking about models in general, we'll wind our way through nonlinear measurement-based models, or end up at the what are some of the most popular topics today, gauging by panel discussions and workshops and that sort of thing, which is the ability to use the NVNA and large signal analysis to generate nonlinear behavioral models. I have a bit of a confession to make. On one hand, I really love modeling. I've been involved with it passively and actively as a user and a generator of models for 20 plus years. And I absolutely love the field, and I'm glad that it's experiencing this renaissance, if you will, because 5 or 10 years ago we couldn't pack a room on a panel session for modeling, but now we seem to do it regularly. The other side of the confession I have to make is that I'm a big skeptic of models in general. Even though I was born in New Jersey, I feel like I'm from Missouri, because I always want people who have models to show me that it's right, show me that it can reproduce measurement, and then show me that I can use it in my design to actually do something maybe not spectacular, but a little bit better than I was able to do before. So as way of background and introduction, that's sort of the motivation for this talk, so that we can explore this brave new world, if you will, of nonlinear measurement-based models. Also, if I slip into some acronyms, I apologize. I will sometimes refer to them as NMBMs, just so I don't have to do the tongue twister every single time. Okay, so at the end of the day, hopefully we'll be able to answer this question, or at least we'll all be able to have a better feel for what's going on here with regard to NMBMs anyway, because there certainly is a lot of activity going on. The agenda for the talk as a whole, we'll wind our way through a short discussion of linear versus nonlinear modeling and analysis. We'll talk about measurement-based models versus whatever the difference is, or whatever the other class of models are. We'll talk about compact models, because that's historically how we've done this. And then we'll go through very quickly in short fashion each one of the most popular versions today, and then we'll close with a summary and conclusion. Okay, so linear versus nonlinear, please don't hold me to greater level of detail than this. I do teach this at the university, so there is a bit more to it. But essentially, it comes down to, in the case of linear, superposition holds. In the case of nonlinear, superposition can be violated, or we're going to allow it to be violated as we vary the independent parameter and look at whatever performance is important to us. Traditionally, we look at this in terms of a P in, P out curve, but it could be simply ramping up the voltage across a resistor. We no longer get superposition. So what's superposition? Essentially, it means that if I put in twice the power that I had before, I'm not going to get the output to scale identically. Or if I put in two signals, that I get the individual response for the two signals through the system at the output that I would expect if I would put in each signal independently and then added the result together. In the case of nonlinear, things saturate, things have power-related functionality that kicks in as we add that second or third signal, or as we ramp up our input power or our drive voltage. Traditionally, what we've done in the RF microwave area is we use S parameters, or we linearize everything. And this is what electrical engineers do in many different fields, is to take a nonlinear problem and simplify it. Even when we do power amplifier design, oftentimes we'll start with S parameters. Why? Because it's easy and it works, and we've done it time and time again. And it's a very comfortable place for us to start. So if we go to our nonlinear device, some sort of FET or bipolar, and we look at what we would do for, let's say, a Class A amplifier. Do I have the point? Yeah, there we go. Class A amplifier. We're going to bias that up right in the middle of the IV characteristics. If we assume a small signal approximation, then that bias condition is going to give us a set of S parameters that will hold for all the different power levels that we possibly could use, or all the different power levels that we would expect to have at the input of an amplifier or a mixer or whatever device we're going to build for that bias condition at that point. If we go to another point on the Smith chart down here, maybe where we're going to bias something class AB or class B or greater, then we would get a different set of S parameters as compared to our nice class A bias point. Now, if we have a class A bias condition in the middle and we put in a very high input signal, clearly we're going to be going from a set of S parameters over here that would be more towards the quiescent point to a set of S parameters over here that would be more towards where we'd be at the high power, peak power point of the waveform as it went through the transistor. So clearly the S parameters are changing. So we would get different gains, different reflections as the input wave went through its 360 degrees of cycle. So clearly in this case, we have nonlinear performance if we're going to have a very, very large waveform going through there. So for us to go through a small signal approximation, if that's the power level we expect to go through that device, is clearly not going to hold, and we would need something that's nonlinear. Okay, so what are non-measurement based models? Well, the best example that I could come up with are physics-based models. So Bob True historically has done a lot of good physics-based modeling at North Carolina State University. Here's a diode model from Chalmers, but essentially rather than using measurement as the basis of your model, you're going to use physical parameters in this example. If there's another way to generate non-measurement based models, I don't know what it is, but potentially there is. Physics-based models are a rather straightforward way. So instead of taking measurements and filling in model parameters, whatever those model parameters might be, we take physical attributes of the devices that we're using. In this case, things like doping levels, junction depths, contact resistances, physical parameters that we can get from the manufacturing process, and we put them into the model, and lo and behold, we're able to predict small or large signal performance. In contrast, our measurement-based models are going to be things like S parameters. Clearly, if we go to a vector network analyzer or scalar analyzer, we could take some S parameters, we can use that as a model. Compact models are another example. We'll get into that in a minute. And then our NMBMs are another one. In the case of measurement-based models, going to that Missouri show-me type of attitude, the risk is really in the measurement uncertainty. That's going to be the basis of all the uncertainty that we would have in a measurement-based model across all the models. Now, the models themselves individually have some risk, and as we go through them, I'll discuss what that added risk is that every modeling type potentially introduces in terms of us using that model to do a design. Okay. So before I actually get into the individual models, we really need to take a step back and understand how it is that models get generated in the first place when it comes to a measurement-based model. The first thing we do, obviously, is take some measurements. The second thing we do is go through an extraction process. And effectively what the extraction process does is it goes from the measurements that we took, whatever that set might be, and we want to do a mapping into our model itself, which is represented by parameters. So somewhere along the line, we have to associate to each parameter in the model a measurement or a set of measurements that we're going to be able to figure out what that parameter is. And each one of these steps potentially is going to add additional risk to our ability to use this model in a design type situation. So we already talked very briefly about the fact that measurement in general is going to add measurement uncertainty. I'm assuming that all of us or who's ever taking the measurements for us does a good job of calibration and knows how to take the measurements in general, but certainly measurement uncertainty, whether it's systematic or random, is going to introduce error into our system. With regard to compact models, all the magic happens in the extraction step. The measurement data is interpreted as the model, and if we're able to interpolate from the known data with the model itself, extrapolation from the parameter set is also possible if we want to do some interesting things like PVT analysis, for example. And then the simulation is just simply grinding through all the equations with those parameters plugged in and whatever input signal is being presented to the device. Okay, the risk with compact models starts all the way back before we ever get to the process where we as the end user or customer of that model are interacting with it. The real risk begins with the model itself. if the model or the equations that define the model don't capture the phenomena that we're really interested in being able to take advantage of or eliminate in our design, then there's really no hope of us being able to design the product or the circuit that we want. So for example, in many early FET models, the relationship between voltage and current had a finite number of derivatives. So how in the world would we ever be able to predict something like the third or the fifth harmonic if we can't take those continuous derivatives? So that's a fundamental limit in those formulations of the model, as a for instance. The second risky area when it comes to compact models is the extraction. We're relying on whoever's mapping the model parameters back into the measurements that A, they have a good mapping routine, and secondly, that they use the appropriate measurements to do that. Additionally, if we don't have sufficient density in our measurement space, if you will, then we're not going to be able to accurately represent all the phenomena that we want to. So again, going back to the example of wanting to get enough harmonics in our model, if we're only taking a very small subset of bias conditions and we start taking derivatives, then we're really going to get into an area where we may miss some very interesting phenomena in terms of the bias conditions, like easy for me to say, minimization points or extrema of second or third harmonic performance. And then finally, we're going to rely on the simulator to take that set of equations and potentially extrapolate beyond that extracted region. Now that extrapolation, again, isn't always with regard to going beyond what the device can do in terms of IV characteristics. It may be going beyond what the derivatives of the device model can do in terms of the model formulation. All right, NMBMs, in contrast to compact models, have a very different sort of flow, if you will. There's still the measurement uncertainty, although because of what we're expecting out of NMBMs or the expectations we've placed on them, the ways that we're exploring using them, the measurements are quite substantial. The new test equipment that we need to do them, I do not want to underplay the complexity of those things at all. The fact that an NVNA does what it does, to me, is an amazing piece of engineering magic that I marvel at all the time. It's just an absolutely incredible gift to us as microwave engineers. But really what happens through the extraction step is that we just reformat the data, if you will, that comes off of the piece of test equipment into something that the simulator can read. And all the magic happens in the simulation because we're taking that data and reinterpreting it into a model. Similar to what you saw in the last presentation, the ability to take that data and represent it into different frequency domains. That's really magical. That's a great way to reduce the frequency set and make some real simulation magic where we couldn't do that previously in a full-blown harmonic balance simulation because we'd have to calculate all those frequencies and derivatives anyway. So all the magic in an MMBM happens in the simulation. With the extracted data being reinterpreted as the model. We're interpolating from known data because that's what we're building the model off of. The model itself is the data, albeit run through a simulator, but we're actually using the measured data to create the model. And in some cases, we want to be able to extrapolate from that parameter set, if you will. In some cases, we want to go beyond or try to go beyond what the measurement space was in terms of input parameters, in terms of impedance conditions, and see if we can get even more out of our models than we could previously. Okay, so one by one, we'll go through some of the more popular ones. The Cardiff model this is the, if you're a do-it-yourselfer at home, this is for those of you who like to measure twice and cut once, or if you wear belt end suspenders just to make sure your pants don't fall down. The Cardiff model is great because they have a very straightforward, very simplistic approach. Not that they're simple models, mind you, but a simplistic approach to modeling, which I have a tremendous respect for as a guy from Missouri, which is let's measure the waveform exactly how we think it's going to be coming into our device. Let's represent it in a way that our simulator can read it, and then let's simulate and design with the very same waveform. Okay? It's a very straightforward way to do things, and I don't want to say that it's a mantra or anything stronger than a basic philosophy, but it's don't deviate from that. That's where we characterize the device. That's where we know it. That's where we have measurement certainty about that device. So let's use that to our advantage. And that, in a nutshell, is pretty much the Cardiff model in terms of the level of detail of this talk. So in one sense, there really is no magic to the Cardiff model. Although again, the fact that you can do these measurements in the first place, measuring tens or hundreds of watts on a device in the time domain to get all that IV data for the actual waveforms is measurement magic. But in terms of modeling, there's nothing really magical about it. Okay, the risks with the Cardiff model. Well, for the model itself, there is no model, so there's no risk really there. We're just rereading the measured data. The typical uncertainty associated with the measurement, of course, is there. And again, because these are complex measurements, we need to be very careful about how we're measuring them and do all the proper calibrations, not just at frequency, but at power and with regard to gammas, termination and source. Extraction, well, essentially there is no extraction because we're just using measured waveforms. So the simulation is straightforward. And I guess just as another euphemism, it's pretty much the WYSIWYG of models. What you see is what you get. If you measure it on the measurement side, that's what you should be able to reproduce on the simulation side. And if it doesn't happen, then maybe you need to go see your simulation provider. Okay, for the S functions and X parameters, I'm a polyharmonic distortion junkie. I love the mathematics. It's beautiful. Thanks, Dave. It's another gift to the industry is PhD, because the math is straightforward, it's easy to understand, but it has this beauty about it that really goes to the heart of how we think and work as microwave and RF designers. What we want to do is we want to measure the device under the desired conditions. Now, in contrast to the Cardiff model, where we have to pick the input signal and the source and load gammas that we want to use, we can relax that a little bit with PhD-based approaches. We want to pick convenient values for doing our impedance and input signal measurement, and we're going to rely a little bit more on the downstream flow of the model to fill in the gaps for us. We're going to rely a little bit more on interpolation. We're going to rely a little bit more on extrapolation, but we don't have to strictly measure everything exactly where we want to use it. So on the measurement side, maybe there's a little bit less risk. On the measurement side, we have a little bit more flexibility. When it comes to extraction of the model, we're just going to use the representative PhD description that we want to use, whether it's S functions or X parameters. We want to simulate the model under design conditions, just like we did with the Cardiff model, but here that design condition doesn't have to map exactly into whatever the measurement condition was. So if things change a little bit, if we want to do something a little bit creative on the input or the output, we have that flexibility with the PhD-based models. So on the risk side, we just need to make sure that the PhD assumptions hold, and we won't go through everything that goes on there. Suffice to say that it's not a big risk at all, and I'd still be much more concerned about the measurement uncertainty, again, because we're taking very nonlinear measurements. We're using test equipment that is very sophisticated. There's no extraction risk, because effectively that's just a reformatting problem. On the simulation side, as skeptics, we need to make sure that we understand the differences between what was measured and how we're trying to simulate it. We need to couch our consideration of the model and its use in that. And that's where a lot of, I don't want to say the controversy, but that's where a lot of the exploration has to go now in terms of microwave design engineers as a community. What can we really do with this type of modeling? How far can we push it? How certain do we need to be of the grid that we're taking the measurements on in both frequency and power? And how much can we push the envelope in terms of input signal and source and load gamma? Just to recap from the compound semiconductor panel discussion, again, this was pretty well attended for compound semi. Where do we have the successes, and where do we need to be putting in a little bit more effort to better understand what we can do with these sorts of models? Well, it pretty much maps into where we have the risk. When we can clearly define the link between design and measurement, when we are measuring very close to where we are modeling and simulating, then people have had great success. When we start to move away from that, when we start to interpolate and extrapolate, that's where some of the issues come in and some of the uncertainties come in. And just quite frankly, I think that just like it took decades for us to become confident of S parameters, hopefully it'll only take us years to become confident of X parameters, S functions, and the Cardiff model as we become more familiar, as we see more design successes, and just as we remove a lot of the unknowns and risk that comes with trying something new. So in conclusion, unpacking nonlinear measurement-based models, We've been doing this for years. The exception to measurement-based models, in the very least, are the physics-based models. Maybe there's another class somebody can teach me about of models that I'm unfamiliar with that don't require measurement. Linear models, S parameters, require measurement. They're limited to where the small signal assumption holds or where superposition holds. But as we grow the input signal or as we get frequency mixing effects, we need to go to nonlinear models, but they require nonlinear measurements. If you think you're just going to do some linear measurements and get a nonlinear model by varying it over bias, well, I guess to quote my daughter, that's so 1980s that you really should maybe think about changing your model type. Compact models are measurement-based. The risk in using compact models or the magic in compact models is the extraction routine and whether the right measurements were done to map those model parameters from that measurement data that you have. When it comes to the new class of models that we've all been talking about for a while now, the Cardiff model is less flexible, but it's low risk. So there's that trade-off there. The idea is that you simulate what you measure. So there's that coupling between what you're designing and what you're measuring. And the philosophy behind that type of model is that the two should align as exactly as possible. A lot more flexibility is available with S functions than X parameters, but with that flexibility, we have to understand what risks we're picking up. We have to evaluate those risks and become comfortable with them as we use them more and more for successful designs. So thank you very much. If there's any questions, I think we have some time.
Question?
Okay.
Forward to seeing hopefully many of you, both speakers as well as audience in Canada.